Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will continue the discussion on Cartesian coordinate system and then talk about cylindrical coordinates and spherical coordinate system. In the previous module we have already introduced the need for coordinate system. We have also told you how one-dimensional, two-dimensional and three-dimensional Cartesian coordinate systems look like. In a three-dimensional Cartesian coordinate system, it's actually an intersection of three planes. One plane can be this z equal to 0. If you move above this plane or below this plane, you are moving along the z axis, let us say. So then there will be another plane which is if you look at my palm of the hand, this would be x and z. So if you move along this line which I am showing, that would be the x movement. You can move up and down to go to the z movement. Similarly, there will be a yz movement here. So if you move like this, this would be the y axis, and if you move up or down, you would be moving along the z axis. Any point on this three-dimensional system can be described with respect to the origin by giving three coordinates. One coordinate will be x, which would be the projection down there, and then finding out the x component and the y component, and the other one will be the z component. So how much along x, how much along y and how much along z, if you move, you would be reaching this particular point in the space will be given by the three-dimensional coordinate system. Now it is something that is interesting that even in a two-dimensional case such as the one that we have considered, x and y, every point can be considered to be not just a point, but we can associate a vector to it. This special vector will start at the origin, okay, or the reference point with 0 and 0 as the coordinates that we have chosen, and then when you extend the line from the origin to the point P with an arrow at point P, then this special vector becomes what is called as the position vector, and these position vectors are either described by capital R or the small r, okay, with a bar on top of it, and this position vector is of course the function of x, y and z. This is a three-dimensional one which I am drawing, but I am showing you a two-dimensional one, but I hope you can understand the connection between the two. This position vector is given by x, x hat plus y, y hat plus z, z hat. So whether you use a notation for capital R or small r, this becomes what is called as a position vector, okay, which means that at every point in space I can actually imagine a line joining from origin to the z point, making a position vector. I also must distinguish another concept with you. Suppose I have, again in the two-dimensional case, suppose I have 2 points. Let us call this point as point P and call this point as point Q. Okay. Now I can have a vector whose head is at point P and whose tail is at Q, that is, it is originating at point P and going to Q. Let us say P is described by x1 and y1 coordinates, Q is described by x2 and y2 coordinates. Then what can we use, or how can we describe this red color line which is actually a vector from point P to point Q? Okay. You can imagine first that we actually draw the position vectors. So there is a position vector from the origin to the point P. This position vector, let us call this as capital P, okay, and similarly I will have a position vector which goes from origin to the point Q, which we will call as Q. Now from the law of addition, you can clearly see that this vector which is joining P and Q is given by Q minus P. Why? Because P plus Q minus P will be equal to Q, which is exactly the vector Q that you are looking for, okay. And in Cartesian coordinate system, how do I describe the vector Q and vector P? The vector Q is given by x2 x hat plus y2 y hat. In case we were considering a three-dimensional scenario, then there would have been a z2 z hat as well, but this is a two-dimensional case that we are considering, therefore there is no z component here. And then what is a P vector? P vector is x1 x hat plus y1 y hat. Now when you subtract these two, you can see that you can individually collect the components and you obtain x2 minus x1 x hat plus y2 minus y1 y hat. Geometrically what this means is that if I project this one, the vector, the red vector onto the x axis, I meet at points x1 and x2, and the difference between x1 and x2 is precisely the length that I have to move along the x axis. Similar will be the case for y1 and y2, although in this case they are not looking very different because the vector is almost horizontal to the x axis. In general, you can have any vector, and the difference in the y that you would have to move will be this particular vector. Okay. Moreover, if you enter red vector here itself, then you can imagine that. So, let us draw another vector out there. So, this is a vector that I am considering whose origin is at P and the ending is at Q, right. If you look at this vector itself, you can actually set up a vector whose length is x2 minus x1 into x hat, which will be obtained by projecting the vector q onto the x axis, correct. So, the length of that projected vector will be x2 minus x1 into x hat. Similarly, there will be a vector that you can set up which will be going in the upward direction, that is along the y direction here, and that vector will be y2 minus y1 into y hat. Okay. And notice one important thing, the directions of the unit vectors along this x2 minus x1 x hat is parallel to the x axis, and the direction of the y vector is parallel to the y axis. In fact, this is very true for a Cartesian coordinate system, that no matter at what point you consider, maybe you consider this point, the unit vectors are always directed along the parallel or directed along the x and y axis, which are parallel. It does not matter where you are located, the unit vectors are always located in the direction. So, they do not change the direction at all. So, this is an important point to keep in mind, because we will see that in the cylindrical coordinate system this will not be the case. Okay. So, now let us move on to cylindrical coordinate system. We consider the two-dimensional version of it first. So, we are now trying to go to a different coordinate system. Why would one want to go to a different coordinate system? The answer is quite simple. There are in some cases, for example, a charge distribution that is present along a certain line, or a current that is being carried by a particular wire. Then the corresponding magnetic field will be in the form of circles which would be surrounding this current. We will be seeing this one as a consequence of Maxwell's equations later on, but any current carrying wire will have magnetic fields which are circling around, and the best way to describe this kind of a scenario is to actually imagine cylinder of maybe different radiuses. So, you imagine that one cylinder is kept inside another of different radiuses. Okay. So, here describing every point in terms of x and y becomes slightly difficult, especially in the three-dimensional case. The easier one is to actually describe the distance r and the angle phi, and whether you are up along the positive z axis or down along the negative z axis. So, in some cases naturally there are situations where a particular coordinate system might be useful. For example, when we are dealing with an antenna, okay, you can see that the fields of an antenna radiate outward. So, the best way to describe this kind of a scenario is not of course a cylinder, but rather a sphere, because the radiation fields start for a simple isotropic radiation antenna, it will actually come out in the form of spheres. So, there one has to go to a spherical coordinate system. So, depending on the symmetry of the problem, you will end up using one or the other coordinate system. The one that would be easiest to use will be the one that is decided by the problem itself. So, we will have a good reason to study this cylindrical and spherical coordinate systems, simply because they will be useful later on. Okay. So, we will look at the two-dimensional version of the cylindrical coordinates and then build up to a three-dimensional version of a cylindrical coordinate. What is a two-dimensional version of a cylindrical coordinate? Go back to the plane. In the plane we had set up x axis and the y axis, and we described this particular point by giving two numbers x and y. These numbers represented how much I moved along x and how much we moved along y. Okay. Consider a different way of approaching this one. I know that I can actually set up a vector here, which is the position vector, and the length of this vector will tell me the particular point where I am looking at. Okay. So, there is a length of the vector which we will call as small r. So, that would be the length of this line segment from the origin. So, from the origin to the point P here. Of course, many different vectors, in fact an infinite number of those vectors will all be directed at the same point. Why? Because you can, for example, consider this green colored vector, although it is not looking like that, but I have actually drawn a circle over here. Okay, this will also have an r, this vector will also be r, this vector will also be r. Okay, that is, the length of these vectors are all equal and they are all r if I draw a circle of radius r here. So how do I distinguish a point P which is sitting on this red vector to a point Q which is sitting at a different point x prime y prime on the coordinate system? Well, one needs to specify a second number in order to completely fix this problem, and that number will be specified by the angle with which this radial vector or radial directed line segment makes with respect to the x axis. Okay. So from the x axis, which I have chosen as the reference, you measure the angle of rotation, and this same point P, which was expressed in terms of x and y Cartesian coordinate systems, can equivalently be by specifying the angles r and phi. Okay, the same thing, but P of r comma phi does not mean that the vector P, the position vector corresponding to P, is equal to r hat plus phi hat. This is simply wrong. Why it is wrong? Well, there are many reasons why it is wrong, but one important reason happens to be that even though I am measuring the rotation, I am specifying the point P by the angle phi, please remember that the units of r is in meters, or it is actually a distance measuring variable. Phi is an angle measuring variable, right? So the units of phi is actually an angle or radians if you want to consider that one. So I can't just find the magnitude as square root of r square plus phi square, just I had done for the case of a Cartesian coordinate system where I took the length of the vector to be square root of x square plus y square. Okay, I can't do this one. In fact, this value is equal to r, which is the radial length, right? And what would be the value of phi given x and y? The angle through which you will have to rotate in order to reach point P will be tan inverse of y by x. Where is this tan inverse relationship coming from? You just drop a perpendicular, clearly this will be x, this will be y, okay, and you are looking for the angle phi from this right angle triangle OP, and maybe this is a Q, point Q. So from this right angle triangle you have phi equal to tan inverse of y by x. Similarly, x in terms of r and phi, that is, if r and phi are given to you, you can find what is x and y. X is simply the value of r projected onto the x axis, right? So that would be r cos phi, and y will be this angle r projected onto the y axis, and that would be 90 minus phi. So cos of 90 minus 5 is cos 90 cos phi plus sin 90 sin phi. Because cos 90 is 0, this is gone to 0, sin 90 equal to 1, so this is nothing but sin phi. The value of y in terms of radial values r and angle phi is given by y equal to r sin phi. In fact, you can use these two equations to go from one point specification in the cylindrical to the Cartesian coordinate system. So this is the form of equations that you will use when you have to convert from rectangular to cylindrical. This would be the form that you are going to use the equations if you want to convert from cylindrical to rectangular. So far we have considered how to represent points on a two-dimensional cylindrical coordinate system. What about the vector itself? In general, I can write the vector P as r hat plus r phi hat, and the magnitude of this vector P will be given by square root of r square plus r phi square, okay, where r and r phi, they are the components of r and phi. But here is something that I want to actually distinguish. Let us go back to the Cartesian coordinate system for simplicity. So I have x and y point here, and I have a point P which will be, say, given by 2 and 2. Okay. What is the position vector for P? The position vector for P is 2x hat plus 2y hat. Now I can also imagine a point Q which would be given by the points 4 and 4. The corresponding position vector for Q is given by 4x hat 4y hat. Now imagine that I actually draw a vector from P to Q, that is, I have a vector which originates from P and terminates in Q. What is the vector that describes this one? Let us call this vector as some vector PQ. What is the vector PQ given by? The vector PQ is given by 4 minus 2 times x plus 4 minus 2 times y, which is equal to 2x hat plus 2y hat, right. But please note here, I have a position vector for p which is 2x hat plus 2y hat. I have the vector pq itself which is 2x hat plus 2y hat, but these two are not the same. They are not the same at all. Why are they not same? Because one is a position vector which is actually given from the origin, right. So, this is given from the origin to the particular point, and the other one is a same vector. I mean, the other one is not the same vector because that vector pq goes from point p and goes to the point q. Okay. So, you have to understand the difference between position vector which always originates from the origin and terminates onto the particular position of a point that you are considering, and a general vector that can originate from p which is not the origin in general, and it can go anywhere it wants. This is a very crucial thing that you need to remember one. Okay. Now, go back to the cylindrical case. On the cylindrical case, I still have a plane x and y. Let us pick a point p which we will label as r and phi. What is the vector that corresponds to this one in the cylindrical coordinate system? Okay. If I want to do that one, I better first convert how to go from one coordinate system to another coordinate system. Okay. And from there I will show in the corresponding cylindrical coordinate system, the answer is not as what you would think. Okay. There is in fact no specification of the value of phi in the coordinators. I am sorry, all the position vectors are directed only along r, which is something that you can see very clearly. Why? Let us see first the corresponding unit vectors r hat and phi hat. On the plane that we are considering, we will do all the calculations in the 2-dimensional plane and then go to 3-dimensional case. So, I am going to consider a point here which would be again r and phi, and now you actually consider the radial direction here. Okay. So, the point P will have some length, but the vector that you can draw from the point here, so you have to see this point. Okay. Let us call this point as P. From the point P, if you draw a unit, in the increasing direction of OP, that forms the unit vector along the cylindrical coordinates. How about the phi vector? Well, you have to draw a circle here, or at least a part of the circle, and then draw a perpendicular or a tangent to this arc, okay, at this point, and this becomes the phi vector. Okay. You can immediately note that both r vector and phi vector depend on r and phi. You are not convinced about it? Let us look at this point here. I am going to consider a point, let us say q, on the x axis. What is the radial vector here? The radial vector will be directed in this direction, so it will in fact be equal to the x vector. What about the phi vector? The phi vector will be directed perpendicular, because phi equal to 0, which means this is the line which is the arc, and if you draw a tangent to that line, then you are going to the phi vector. You can see that the phi vector is actually equal to y and the r vector is actually equal to x. So, you see that just between points q and point p, the direction of the r vector and the phi vector themselves are completely different, because they actually depend on the values of r and phi. Okay. This fact will be very useful when we want to specify or when we want to find out the corresponding values of r and r phi, and therefore formulate a cylindrical coordinate vector over here. In fact, we will show that for this particular red vector that we have drawn, the corresponding value of r phi will be equal to 0. Okay. How do we do that? Let us examine the relationship between the phi vector, r vector, that is the unit vectors, and the x and y unit vector. So, this is the r. So, from this point, let us say this is the r vector, and then this is the phi vector. These are the unit vectors that we have drawn, but at this point I can also construct the unit x vector and the unit y vector. Okay. And what is the angle between r and x? The angle between r and x is phi. The angle between r and phi is 90 minus phi. The angle between y and phi is phi, and the angle between x and phi is 90 plus phi. Okay. So, let us say the angle between x, y, r and phi, just to put it into a table so that you can easily read off, the angle between r and x is phi, the angle between phi and x is 90 plus phi, because there is a 90 degree to go to y and y plus y to phi, phi degrees. Okay. r and y will be 90 minus phi, and phi and y will be equal to phi itself. Okay. Now I know how to specify, so let us call this point as P, right. So I know how to specify the position vector P. How do I specify? Well, I know what is the values of x and y at this point. So there are those generic x and y points. So I can actually specify this as x hat plus y hat. But I want to now specify this one in terms of r hat plus r phi hat, okay, where r and r phi are the components along r direction and the phi direction. Okay. So physically these two are supposed to be the same because they are just the same point, so that is the same vector. It does not matter whether I am considering the vector in the Cartesian coordinate system or in the cylindrical coordinate system. However, I know that I have written down these two. My aim is to find r in terms of x and y, r phi in terms of x and y. How do I do that? Let us go back to this equation. So let us call, this is a position vector P, right. So I will write this one onto the left hand side, okay, and then dot by r throughout this vector. So when I take the dot product, I already have seen in the Cartesian coordinate that x dot x will be equal to 1, y dot y will be equal to 1, x dot y which is equal to y dot x is equal to 0, right. So when I take the product, in the similar way, if you replace x by r and y by phi, you will essentially get the same relationships, that is r and phi are perpendicular to each other, which is very well known from this particular thing, right. So now if I take the dot product here, what I get is r, but if I now go to this vector P which is in the red vector and then take the r or the dot product with respect to r, what do I get? R dot x hat plus y hat. I know what is r dot x hat, I know what is x, right, x is just x here in this case. What is r dot x? R dot x will be unit magnitude, but it would be cos phi. So I will have x cos phi plus r dot y is basically cos of 90 minus phi, which we have already seen to be equal to sin phi. So this would be equal to y sin phi. Okay. Similarly, if I take the product with respect to phi hat, then I will get r hat plus r phi hat. This would be equal to r phi component, and now you have to go to phi hat dot x hat, right. So here it would be phi hat dot x hat plus y hat. So this you are going to get as x times, what is phi dot x? Phi dot x will be cos of 90 plus phi, and that would be minus sin phi. So it would be minus x sin phi, and you will have for the component for y, phi dot y will be equal to y cos phi, correct. So I have got these relationships for r and r phi from here. Okay. So we see here that r is given by x cos phi plus y sin phi, r phi is given by minus x sin phi plus y cos phi. But our job is not complete here because I need to replace x and y by the corresponding values of r and phi. So at the point where I am considering, I know that x can be given as r cos phi and y is given as r sin phi. So what will happen to the component r? So this becomes r cos square phi plus y is r sin phi. So this becomes r sin square phi, which is actually equal to small r. Okay. What will happen to this fellow r phi? You can see that when I substitute for x, the first term becomes minus r cos phi sin phi plus the second term becomes r sin phi cos phi, but one of them is carrying a negative sign, therefore this becomes equal to, or this becomes 0, right. So what we have just found out is that if I go back to this picture that I have, x and y is the plane that we had considered, and we were considering the position vector of P. In Cartesian coordinates, the position vector was given by x hat plus y hat, because this point P is described by the points x and y coordinates in the Cartesian coordinate system. But the same point P is described in terms of r and phi. Okay. In this case, what we have just found out is that the corresponding component r phi will be equal to 0, while only r will be equal to r. So the correct position vector for point P in cylindrical coordinate system is given by r hat. There is no phi hat component over here. Okay. It does make sense because r will only give you the increasing directions of r, and now if you imagine that you can actually draw a circle, the direction along increasing r happens to be the direction of P itself, right. There is no phi component required to specify P. But you should not hastily conclude that r phi will be equal to 0 all the time. There are many cases when r phi will not be equal. To show you that, I won't derive it here, but you can see that if I consider a general vector which let us say goes from point P to point Q, okay, then this general vector cannot be written just a component with just r. Here r phi should be non-zero. Why? Because you can again imagine that there is a position vector in the cylindrical coordinates. There is one more position vector in the cylindrical coordinates for P vector and the Q vector. This difference vector is still Q minus P, but you cannot now just go back and say no r minus r. Okay. So in case what you will be generating is a totally different r. Okay. The correct way to solve this problem in the cylindrical coordinate systems, which is also the hard way, is to first convert this P into the rectangular coordinate system, convert this Q into the rectangular coordinate system, then take the difference. Okay. That difference that you obtain will be in the rectangular coordinate system. After you have taken the difference, you can again go to cylindrical coordinate system. There you will see that r phi will be non-zero. Okay. A geometric way of seeing the same thing will be to remove these red colored position vectors, okay, and then just imagine that I have this general vector, right. So which was going from P to Q, and if I initially consider going along P, so I will start my journey at P and go in the increasing direction of r. The increasing direction of r for point P will actually be along this direction. So I might go up to this one. So there is a circle here and then there is a circle here. So I have actually gone up to this point, right. So let us call this point as capital R. I have moved a certain distance, let us say this certain distance I have moved is along R, but I do not reach Q, I reach a different point R. In order to reach point Q, I have to then move in the direction opposite to phi, go over this distance which corresponds to whatever the radius of this Q point circle that I have drawn at Q times the angle through which I have moved. Okay. So you do see that r phi and r both can be non-zero, but for position vectors r phi is always equal to 0. Okay. So that is the difference that you should keep in mind. Okay. We now quickly extend it to 3-dimensional cases. We talk about represent a point on a cylinder. Okay. You can imagine that I actually have a cylinder which is kept along the z axis, okay, and from there I can try to find out any point in terms of the cylindrical coordinate system. So let us say I find a particular point over here, and then the radial distance of this point, okay, will give me the point on the cylinder. Okay. So if I have done a cutaway from here, I should actually have written a nice cut along this axis, but anyway it does not matter. So in the 3-dimensional case, the 3 values which are going to tell me what those values are given by the radial distance r from the point, and then the height z, and then the angle phi, because on a 3-dimensional case maybe the diagram was not very nice. So let me redraw it again. So you have to first consider point r and then project this point, and from the projected point consider what would be the angle phi, okay, and this would be the z axis that you are going to see, and this entire thing would be the point or the radial distance that you have considered. So the radial distance is actually coming from this point. So this is the radial distance and this is the height over which you have considered or which you have located the point, and if you now drop a perpendicular onto this axis and the angle with which this line, this red line makes with respect to the x axis will give you the angle phi. Okay. So you have these 3 variables to actually tell you the corresponding values. At the same time, how are the 3 different unit vectors oriented? The unit vectors are oriented along r, so this would be along z and this would be along phi. So this would be along phi over here. It's the diagram is not very nice, I will show you a proper diagram. So these are the 3 directions of r, phi and z. Maybe slightly better way to illustrate that entire thing is to look at this cylinder over here. So I have this cylinder over here which is representing a constant radius r, okay, and this axis will be the z axis. Any point on the cylinder, you can look from the top here or you can see from this point. Let us call arbitrarily this particular circle to be located on the x and y plane. So it is as good as you are taking some kind of a blade and then cutting it off here and measure this height, okay. So if you measure this height, you are going to measure the value of z, and if you start from this center of the origin and then draw a radius, so you can actually imagine that there is a this particular pen is coming out, the length of this one will be the r direction, and this would be the direction in which r would be continuing, and this is the z axis. And then if you project this point down to this x and y plane and then measure from this one, so let us say this is the x axis that I have, measure how much or what is the angle that this projected line makes with respect to the x axis. That will tell you the corresponding value of angle phi, okay, and this would be the direction in which phi is increasing. So that is the unit vector direction. This is the direction in which z is increasing, therefore this is the unit vector along z, and this is the direction in which, so you can imagine from the top and then you are going like this is the direction in which the r vector is located, because you can open up this cylinder and then make the radius of the cylinder larger and larger, okay. So you are actually expanding in this particular direction. At this point, I would also like to introduce couple of other vector elements which we have not done so in the Cartesian. We will first show it in the cylindrical coordinate system and then go to the Cartesian coordinate system. See, suppose I am having this particular cylinder, I start at a point which would be some r, phi and z, okay. If I move along this line along z, so if I move along this line here, that will correspond to movement along z axis, right. So if I move a unit of some dz along z axis, a small distance dz along the z axis, I can represent that movement as a small vector, okay, or the movement or a line vector dz z hat, okay. So as I have now moved at a small distance dz, if I start moving along this circle of a constant radius, then I will actually be moving along the phi axis, right. But distances along phi movement along a circle, when you move a distance of phi, will not be measured by the amount of angle itself, but that has to be multiplied by r. So the same angular movement on a shorter cylinder radius will give you a shorter distance than the same movement of an angle. So if you move 30 degrees on a shorter radius, you will move a smaller distance, but the same 30-degree movement on a larger radius will give you a larger distance. So the movement along phi is actually given by r d phi, where d phi is the angle through which you have moved and r is the constant radius that you have. And you can now actually imagine that I have completed this particular movement, move back along the dz direction, move back to the starting point. What I have done is to generate this curved surface area, which when you observe very closely would look like a small plane segment, okay, and this plane segment will be oriented. We say that the orientation of this plane segment of area r d phi dz will be along the z axis. Similarly, if I move along phi, but then imagine that I am expanding this radius, okay, then I have moved a certain distance along phi which corresponds to r d phi, and then I move along a certain distance this is actually the movement along r and z which I want to illustrate. So first I expand the cylinder, so I move a small distance dr, okay, so that is dr along r, and then I move a certain distance dz. So again you can imagine that I am moving along dz while simultaneously expanding this one to r. So the current, the loop that I am going to obtain, which would be like this particular loop, that would be oriented along the phi axis, and you would had a area earlier dr and dz, okay. So what you are generating are what we call as line segments and the area segments or the surface areas. Let us go back onto the board and then show you what exactly that I was talking about. So I have this cylinder, right, of some radius r that I had. So if I continue to move along this value r, I would be moving to a new point which will be represented by r plus dr. All the other points are the same. So all the other points are the same points, okay. However, this movement from r point to the r plus dr point can be expressed in terms of the unit vector along r. So this movement is actually a vector movement given by dr r hat, which tells me that I have to move along r direction by an amount of dr. If I move along z, so I move a certain distance dz along z axis, I can consider this movement. So I would be landing from z to z plus dz point, right. So I would be landing at z plus dz point, and I would have moved a distance of dz z hat. Now if I consider dz dr to be the product, over which I have actually moved, and then what I will actually get is this particular surface area. What I am actually forming is what is called as the cross product, okay, and this product will be oriented along the phi axis. So the magnitude of that cross product will give me the area or the infinitesimal area, which would be coming out of this plane. This would be along the phi direction, okay. So this particular infinitesimal surface area in which phi is constant, I mean movement along z and r, is called as the surface element or the surface area, which is oriented along the phi axis, and this would be a vector surface area, which means that you can associate a vector to the area. Area being a scalar, you have actually associated a vector to that particular scalar, okay. Similarly, you can imagine moving along r and then moving along phi, but if you move along phi, you would be moving a distance of r d phi, okay. Moving or dr along r axis would have given you this one. Now if you complete this movement at a constant z, so at z equal to constant, what you have just done is to obtain the surface element which we refer to as dsz, and this is given by r dr d phi oriented along z axis, okay. Finally, if I can move r d phi along the phi axis, right, so I have actually I need to now find out what is dsr, right. So I can move r d phi on the phi axis and then move a distance of dz on the z axis. So when I do that, what I will get is this element which is oriented along the radial direction. So these are three surface elements which represent phi equal to constant, z equal to constant, and r equal to constant surfaces. So along these surfaces, if you move a certain distances, then you would be generating an equivalent amount of oriented vector elements. This is very important when we consider the surface integrals later on, okay. Similarly, I can show the surface elements oriented in the Cartesian coordinates for the x axis will be given by moving a distance of dy along y axis, dz along z axis, and this would be oriented along x. Similarly, dsy will be equal to dx dz along y, and then I have dsz to be equal to dx dy along z, okay. So these are the three surface elements. Incidentally, I have moved a certain distance along r and along z, and also I have moved a certain distance which I did not write here, but I have moved a certain distance of r d phi along the phi direction. So this is these three movements which are moving along the specified directions along r, phi and z are called as line segments, okay. So I have actually moved in an oriented way along r direction, z direction and the phi direction. So these are the line elements. So you can call this as dlz, this as dlr, and this as dl phi, okay. And in fact, if you move a distance of dl phi, okay, and move a distance of dlr, move a distance of dlz, you would have actually moved from a point r phi z to r plus dr, phi plus d phi, and z plus dz. So you would have actually moved from this point, older point, to a new point, okay. In this case, you can see that the corresponding vectors can also be written, so or the corresponding line element movements are very similar to what we would have seen in the Cartesian coordinate system, except you can think of this as dx hat, dy hat and dz hat, right. So here you will be thinking this of dz z hat plus dr r hat plus r d phi phi hat. So you can see that this is actually a vector in the cylindrical coordinate system with rz given by dz, r given by dr and r phi given by r d phi, okay. So this is how you can construct a line element and go from any point on to any point on the cylindrical coordinate system. But do not make a mistake of combining these and thinking of this as a vector, okay. So this is not a vector, okay, because these are areas. You can't combine areas which are pointing in 3 different directions or into 3 different things and then try to combine them into a vector, okay, because here you can move the vector. This is not a proper vector, so this is not a correct vector to talk about, whereas this is a correct vector, I mean something that would be useful in the line integrals. Okay, before we break off from cylindrical to Cartesian coordinate system, let us look at the full process of converting from cylindrical or Cartesian and back. Okay, we have already seen a glimpse of this when we converted the position vector, but let us carry out the analysis in 3 dimensions and complete this process. Okay, suppose I have a vector p which is described by giving the elements along x, y and z. So, it has the components of ax, ay and az. Okay. Let us also assume that the same vector is given by r hat plus r phi hat plus r z hat. Okay. How do I go from this Cartesian coordinate system to a cylindrical coordinate system? Well, again I would consider these vectors p dot r, p dot phi and p dot z, right. When I do that, I will in between be trying to find out what is x hat dot r, y hat r, z hat r. Because of the dotting of phi with respect to p, I will be obtaining x dot phi, y dot phi and then z dot phi, and then I will have, because of p dot z, I will have x dot z, y dot z and z dot z. Okay. So, once I find this particular matrix kind of a thing, if you can imagine, this will be, what is this p dot r vector? If you go back to this equation which is expressing the cylindrical coordinate system, this will be equal to r, this would be equal to r phi, this would be equal to rz. So, what you have is a vector whose components are r phi and rz, which you can arrange it in the form of a column vector. Then there will be this transformation matrix, okay, which will consist of the inner products or the dot products of these elements multiplied by whatever the values of ax you have, ay you have and az that you have. Okay. So, what is the matrix here? X dot r we have already seen, this is nothing but cos phi, this value is sin phi, y dot r is sin phi. What about z dot r? Luckily for us, z and r are perpendicular to each other, therefore this would be 0. X dot phi we have already seen to be equal to minus sin phi. This y dot phi we have already seen to be equal to cos phi, and then this is 0. X dot z is 0, y dot z is 0, z dot z is 1. So, given any vector with ax, ay and az, you can use this matrix to get to the values of r, r phi and rz, and further write x as r cos phi, y as r sin phi, z of course is the same z. So, if you use these relationships and the values ax, ay and az, then you can construct the vector p in the cylindrical coordinate systems, which will have r as the r component, r phi as the phi component and rz as the z component. You can actually try this example with the position vector itself, that is, if I consider the position vector x, y, z, meaning ax equal to x, ay equal to y and az equal to z, you will see that the same vector p in the cylindrical coordinate system will be described by r hat plus z hat. Again, there won't be any phi into the expression. Okay. So, you can do this one transformation, transform the cylindrical or rectangular into cylindrical. You can actually go back and do the same thing. So, you can go to case of cylindrical to Cartesian coordinate, you just have to invert this particular matrix and replace phi by tan inverse y by x, r by square root of x square plus y square, and z of course will still be equal to same value of z. Okay. So, to summarize, in the Cartesian coordinate system, which is formed by 3 mutually perpendicular axes x, y and z, the point where they all meet is called as the origin. Any point p can be described by the 3 points x, y and z and a corresponding position vector p, okay, which will be described by ax, x hat plus ay, y hat plus az, z hat. If you move a certain distance along x, y or z, the line element in the 3-dimensional coordinate system will be given by dx x hat, okay, plus dy y hat plus dz z hat. Similarly, the surface element will be given by, depending on which surface you are considering, the x element will be given by dy dz x hat and so on. Okay. For the cylindrical coordinate system, before we go to cylindrical coordinate system, there is one more element, which is the volume element, which is given by dx, dy and dz, and luckily this is just a scalar for us. Okay. So, if I go to the cylindrical coordinate system, I am describing this one by 3 coordinates r, phi and z. Okay. So, r, phi and z. So, any point P can be described by 3 points r, phi and z. Again, we have seen what is the line element. This would be r, or rather dr r hat plus r d phi phi hat plus dz z hat. You can also write down what is ds r, ds phi and ds z as the 3 oriented area elements, and the volume is of course given by r, dr, d phi and dz. Okay. So, this is the rectangular and cylindrical, and there are matrices which allow you to go from one coordinate system to another coordinate system. We will not talk about the spherical coordinate system simply because the corresponding elements are slightly complicated. So, I will refer the textbook for you to understand the spherical coordinate system, the corresponding lines, surface and volume elements. Thank you very much.